And we're going to do this by simulating the tree structure using an array and some clever math, or in languages that will allow this, a dynamic array, a dynamic list, and some clever math. So let's consider this heap here. Okay, if we're going to store it linearly, our root goes to index 0. And our left child of the root 4 can go to index 1. And then our right child of the root goes to index 2, and so on and so forth. And we continue across all levels, moving across the level and then down to the next level as you complete the previous one. And we end up with this, which you notice will be the order of traversal if we do a breadth first search of this tree. This is not an accident. But there's some fun things here. Do we see a pattern in this? Okay, 4 and 5 are the children of 0. And 6 and 8 are the children of this guy. So this means that we have an index of I for a current node. We can find our left child by multiplying our index by 2 and then adding 1. And we can find out the right child by multiplying by 2, adding 1, and then adding 1 again, adding 2, right? 2 times 2 is 4, plus 1 is 5, plus 2 is 6. The system works. 0 times anything is 0, plus 1, plus 2. Okay. How do we go back up the chain? How do we go from 6 or 8 back to 5? Well, we could do some logic, right? We could say, okay, well, if it's an odd number, right, all of our odd numbers are going to be our left children, right? These are all left children. So if it's odd, we can subtract 1, and if it's even, we could subtract 2, and then divide by 2, and that would work. That would absolutely work. We can also get creative with some math, right? If you notice, if we just subtract 1 and divide by 2, right? So let's do this. Let's get rid of this. If we subtract 1 from each of these and divide by 2, we get 0 or 0.5. And then we get 1 and 1.5. And then we get 2 and 2.5. You notice this pattern? 3 and 3.5. The integer portion is always accurate. So we just want the integer portion of this math. Hey, why don't we just do integer division? If we do this, it will strip off our decimal point. And we'll be good. So we can do that. What are the benefits of this? What are the benefits of this approach? Well, math is fast. All that math that I just did is really fast. So calculations are big O of 1. Our structure is static and contiguous, right? And if you think about it, when we add children, we're just going to be adding them out here after our current. So that's nice. It's compact. And if we have a heap of size n, right, adding a new node is just adding at index n. Right? The heap pictured has n of 9. So we just append onto the list, which is, you know, in Python, a dynamic array has additional slots after the end that are just there, right? It resizes as needed. So it just goes, okay, well, let me put it in the next available slot. It's a big O of 1 process. Removing an element requires swapping index 0 and n minus 1, and then removing what's at index n minus 1. So this is fast, and we can get to any slot in big O of 1. The calculation to figure out where we need to go is big O of 1, and random access of an array is big O of 1. We are in perfect shape either way.